Hey everyone, welcome to the Transformative Vertical Flight Working Group, Public Services Meeting number 86. Today is Thursday, May 30th, 2024. We're going to spend a few minutes talk about the agenda, the upcoming meetings and conferences and so on. And we have a very special guest, Dr. Wagter from the Delft University of Technology in Netherlands. And I'm going to, after the initial startup session, I'm going to ask Dr. Marilena Pavel to introduce our speaker. They know each other well, so that's much more effective way to introduce our guest speaker. So quickly, let me bring up the next slide so you can see, again, we're not trying to cover all the possible meetings out there, but I try to each time bring up a few that either kind of unique or kind of interesting or most likely interested to our members. The forthcoming one on the upper left-hand corner is the ASTM F-37 Committee June 2024 meeting. It's going to take place at Advanced Aircraft Headquarters at Aurora, Oregon. This one could be very interesting because a lot of discussion is going to center around the Mosaic, the upcoming rewrite of the light sports aircraft category rules that generate a lot of possibilities. So this meeting is uniquely important, especially on some of the more compact units that can be used for public services missions. On the right-hand upper corner, there's a June 10th to 12th. It's a virtual meeting, so anyone interested should be able to log in. It's a conference on EV infrastructure. There's two tracks. One is talk about the deploying EV infrastructure and fleets. The track two is about design and manufacturing of charging systems. It's sponsored by the Charge, the technical magazine that I happen to subscribe to. That one is interesting because I think the two, for disaster relief, humanitarian aid, emergency response, quite often we need to rely on not a fixed-based service stations. Perhaps if we can do a round trip, that may be fine, if we base at a hospital or something, or a police station or the fire department. But in many cases, we need to be deployed further or one-way range capability stretched to the extent. If we do that, how do you recharge? Like disaster relief, how do you recharge out there? How do you deploy the whole fleet? Can you take advantage of the EV infrastructure to support the different kind of missions? So this could be an interesting online meetings. And a big one, of course, is the 18th Annual Electric Aircraft Symposium. It's going to take place July 20th, 21st in Oshkosh, Wisconsin. Guess what? Right before the world's largest flight gathering, EAA Oshkosh 2024. Same place, same time, just right before that. So many of us is going to be there. Looking forward to see some of you out there. The conference has always been good, interesting, informative. So I will encourage that if you plan to or thinking about going to Oshkosh, make sure you get there a couple of days earlier to attend the symposium. And of course, needless to say, the EAA AirVenture Oshkosh has always been amazing. You can always find all kinds, from antique airplane to fighter jets to transport aircraft to civilian, Cessna 172, private airplanes, airliners, anything you can think of, kit airplanes, eVTOLs, anything you can think of that flies, probably going to be there. So If you haven't been there before, strongly encourage the participation, engagement there. So the next one forthcoming is right after that is July 29th to August 2nd. It's a AIAA Aviation Forum. It's one of the largest two AIAA meetings. A lot of technical papers report. It's more technically oriented. One of the important aspects is it also includes the EATS, the Electric Aircraft Technology Symposium, taking place the same time at the same place. As part of it, that could be quite interesting to many of our members. So I will again encourage everybody to. I'll be there. So join me at Las Vegas. Now, on the left-hand lower corner in August, there will be a summit called the eVTOL Summit 2024. It's going to take place in Los Angeles, California. I'll be one of the speakers. So if anybody in the West Coast, that would be a good place to visit. Or if you're not in the West Coast, it's a good time to take a vacation in that direction anyway. So encourage you, and if you're going, please look me up, and I'll be more than happy to brainstorm with any of our members, and I'm sure we can come up with more creative ideas and that can benefit the public service missions. That's some of the, anybody else has something of interest, could be interesting to our members? Any conference in Asia or in Europe that you guys know of? All right. Now, one thing I would like to suggest that if anybody know of a forthcoming 2-3 months of meetings that could be interesting, regardless, especially in addition to what's taking place in North America, please send it to me a few days before our follow-up monthly meeting. That way I can incorporate them into our listing here. That would be great. Yeah, this is a global membership operation, so I think we need to make sure that we don't forget about conference and meetings beyond this. Okay, now with that, any other things that we should cover at this point, or the rest of the topic we can cover after our keynote speaker's presentation?
Hey, Johnny, it's Bruce Cogan from NASA. Real quick, I'm putting a link in. Just saw this release. Some folks may have had this. It's out of NASA Langley. It's the Generalized Urban Air Mobility Simulation. Basically, it's an open source on GitHub, open to all, high fidelity flight dynamic simulation of an eVTOL urban air mobility vehicle, kind of using for studying autonomous flight and such under real world assumptions. Source code Simulink models and description are included in version 1.1. I can't put all the background there, but I do have the link. Irene Gregory at NASA Langley is running this effort, but they hope to have folks using it, collaborating it. Apparently there's going to be some challenges for researchers and such. So encourage everybody to take a look. The only ask, it's free open source, but if you're using it, please let Irene know so that in the future she can get some more funding to add enhancements.
Oh, that's great. Good news. Thank you. Thank you very much. As a matter of fact, if you don't mind, also email me the link as well. But the one thing I'm thinking about, maybe what we can do is create a resource page. Just put it in our. We still have a NASA Google Drive for our working group. As I collect those, I can put that in a resource page so that anybody, our members, can access. This will be a good example of what that can be. So thank you so much. Yeah, thank you very much.
Yes, sir. In your email, and this is, I did confirm open to all, including all our colleagues at TU Delft.
Oh, good. Good deal. Thank you.
Mm-hmm.
All right. All right. With that, I'll tell you what. Let's get to our keynote speaker. Dr. Pavel, would you like to introduce our speaker?
Yes, good evening from Delft. I have the pleasure to introduce my colleague, Christophe De Wagter. So, Dr. Christophe De Wagter. I work with Christophe since he graduated in 2005, 2004. I work in the control and simulation, and Christophe works in the drones group, the micro air vehicle lab. Christophe has many achievements in the area of drones since he graduated in Delft 20 years ago already. Christophe, incredible. He has an interest in control theory and computer vision, conceptual design and artificial intelligence in order to make all the drones that they are designing flyable. He has novel concepts they are testing with, so Christophe and his colleagues are testing many new different flapping wings, Delphi robots, tail-sitter UAVs, Delftacopter, another drone. Probably he will talk about all these. In this time, he has also has experience as private pilot, glider pilot, certified drone pilot, and I think he's busy with safety management for the MAVLab. The group of MAVLab here in Delft has many achievements, many prizes, and Christophe has put some of the achievements of the group. And one of those, I think there are in last one was 2018, the best MAV. 2006, second place for the drone race, and many, many others achievements. So, Christophe, thank you for being online. I know that this evening, and thank you for talking to us. So, looking forward to your talk.
Thank you so much for the introduction. If I can get permission to share, then I'll try to get my screen up. So now I have permission.
Please go ahead.
I hope we have no technical difficulties today. Can you see something?
Yes.
So the topic of my talk is a group is trying to regroup some of the developments we made that are related to vertical flight. I didn't know exactly who was going to be in the meeting, so I hope I selected things that are nevertheless of interest to most of you. And the topic is hover and fast flight, which we try to combine here at the MAVLab of minimum mass. We're called micro for a reason, but always mission capable flying robots. We try to make flying robots. Next slide. Okay. So the topic is flying robots. I don't have to go in great detail of what they're used for, whether it's inspection of the vast amount of infrastructure all over the country, flying far out at sea and inspecting a windmill is some of the applications we're looking at, but also bringing a defibrillator while quickly navigating around obstacles in a city. We think it should be part of the achievements of the future. And of course, package delivery is highly discussed and already applied at many locations. But if we look at nature, we think we still have a long way to go. Here we have a beautifully hovering little bird, which is then flying off after it got some new energy from the flower, is flying pretty fast and pretty efficiently. If we look at the flying robots we are having today, we think there's still a long way to go. And I would like to show some of the achievements we had that are related to this. We think for many applications, flying robots will need to be able to hover, whether it's for inspection or delivery, for landing on a ship or in a small area within a forest. Hovering is paramount. But a lot of applications also require long distance or fast flight. If you want to bring a defibrillator, you'd better be fast. A rapid aid if you're flying too slowly, it's going to take longer, which also requires more energy. And we want to fly longer missions. Unfortunately, these two are pretty incompatible, conflicting. And at the MAVLab, we try to focus on also minimizing the mass. A lot of applications can be solved with a bigger device, which is great, but we think for some applications, you have an advantage when you're smaller. For instance, if you're in the vicinity of people, the safety can be an issue. Cost is typically less for a 1 kilogram than a 100 kilogram flying vehicle. The use of energy in aerospace is a very recurring important topic, which can also be addressed with minimum mass, which is why we put it in our requirement list and even in the title of our lab. And we want robots that can actually do something. So always a top-down approach to keep mission-capable autonomous platforms. So I would like to look at this combination of hover and fast flight from several dimensions. The first is efficiency. What would it look like if you want to achieve the ultimate combined hover efficiency and forward efficiency? What would it look like if you're trying to merge these requirements into a flying robot, but you're mainly focused on endurance? What would it look like if you try to make the smallest possible platform? And last but not least, if you need to navigate very quickly through very complex environments, then yeah, what speed of flight can be achieved? But first, efficiency is not unimportant in aviation. And yeah, how do you combine efficient hover with efficient flight? We tried a lot of things, but the most efficient way of flying forward, flying from A to B, is wings. The most efficient devices are probably gliders. They can have lift-to-drag ratios of easily over 50, which means they use very little energy to stay in the air. These wings are very efficient for going from A to B. But they cannot land vertically, so therefore a big rotor, slow-turning rotor, is the theoretically most efficient solution. Actually, theory says probably a single-blade rotor would be the optimum, but it comes with so many drawbacks that it's not often done. But these requirements are very conflicting. So let's have a look at a few possibilities to combine them. Of course, we started with the simplest. So a quadcopter, 4 propellers, is a very easy solution to hover, a very popular concept. If you just add a wing, you have a device that can hover and fly fast forward. But the propellers you need to hover and to fly forward are very different. You would want a small propeller with a high pitch for fast flight, a very big propeller with the low pitch for efficient hovering. And here, the tail-sitter concept kind of forces us to reuse the same in both regimes, which is not optimal. So in the next iteration, we had an aircraft with very big propellers that could fold for the hovering, and small propellers for forward flight, which were placed at the wingtip so that the wing vortex was counteracted. You won a little bit of energy. This actually turned into a company, the Atmos UAV. But yeah, if you optimize more for cost, having 2 propellers is more efficient than 4. So leaving out the 2 tip motors, but adding big aerodynamic flaps behind it to do the pitch and yaw control also works. And you end up having a slightly lighter vehicle. But again, you're using the same propellers for forward flight and hover, which is not efficient. So what is the ultimate solution? Well, a very big rotor, which can have a small pitch angle for hovering, and then for forward flight, transition the entire platform 90 degrees and use the same rotor, but at much lower RPM and much higher pitch to fly super efficiently forward, while the entire mass of the of the vehicle is lifted by the delta wing. This is the so-called Delftacopter. It's fully electric. It was designed for a competition where it needed to fly 60 kilometers in normal outdoor conditions with 25 knots of wind. And we were the lightest participant in this competition. Most participants had 20 kilogram vehicles, and we only had a 4.3 kilogram electric platform, thanks to the amazing efficiency. It didn't go easily because this big rotor combined with a big wing interacts heavily with each other. So we are basically steering two vehicles at once, a collective and cyclic pitch controlled helicopter rotor with a fuselage behind it. Probably most of you know that the gyroscopic disc, if you apply a pitch moment, then it rolls. Well, if the wing applies a pitch moment, so if it uses the elevators, then it means that instead of pitching up, like it does with a normal fixed wing, it would yaw. So complex control and aerodynamic interactions. Here's a little illustration of a test flight where we try to excite all possible eigenfrequencies. And you see at some point that the rotor and the fuselage are out of phase. And that was a very interesting challenge to solve, but it worked out. Here's our participation in the competition. Normal windy day in the Australian outback, a lot of lift under the clouds, so turbulent conditions, vertical takeoff, and then a swift transition when it reaches its 60 meters height to forward flight. Thanks to this big rotor of a relatively light platform, we are very efficient at hover. And once it darts off in forward flight, the rotor slows down and the platform then flies very efficiently forward. To show it's a full robot, it has computer vision on board, can find the landing patterns and land on it, deliver the payload. If this isn't enough, we were flying with batteries here, then if we want more endurance, we have to do something more. We can, of course, wait until better battery technology comes around. But if we want it now, then another solution is to replace the energy with alternative sources. We still wanted to do electric flight, so we designed a different type of optimized hover and fast flight capable platform around a fuel cell, an electric fuel cell that converts hydrogen to electricity. And as a hydrogen source, we selected compressed hydrogen because that allows us to generate it on the spot and compress it into the bottle and store it for a long time. If you have liquid hydrogen, it's slightly more difficult. On the right, you see some testing of this fuel cell, and here some more testing, seeing that there's no leaks, and how much power we can get out of this system. And power here is really the problem. So we have a lot of energy, but we have very low power. So we need to be still very efficient to fly. And for the non-efficient phases like hovering, you need something extra. The other problem is safety. We had to go through rigorous testing, for instance, dropping these pressurized hydrogen cylinders to see what happens. It turns out from up to 50 meters on concrete, they bounce like a basketball, but the metal parts tear apart and then they leak and they go inert after the leak is all the hydrogen's leaked out in a minute, and then they're safe to approach again. Set up some procedures, and then we're ready to design a drone around it. But how? What's the optimal shape around a pressurized hydrogen cylinder? Tried a lot of things as illustrated here. You want a tilt wing or a tail sitter or an inline or something in between. And we ended up selecting this. A tandem wing configuration with an efficient fuselage around the fuel tank with the fuel cell in the back, some extra air inlet, because fuel cells, as you might know, create more heat than they create power. So for every watt you use, it creates at least a watt of power of heat as well, which needs to be evacuated. It's a tail sitter with a lot of propellers for redundancy, which is needed in order to fly here in the Netherlands and get the required improvements, the required permits. And yeah, it combines the fuel cell with batteries, because fuel cell alone is not able to deliver the power needed for hovering. So electrically, it's also challenged to recharge in flight, etc. There's a few images of what it looks like. Somebody putting the cylinder in. This is for cinematic purposes, but in practice, you would attach the cylinder, and then you can take off, for instance, from a ship and land and fall back on its nose. The tandem configuration has to do with the fact that we want the smallest wing as possible. So having two makes them slightly, gives them slightly less wingspan. And because we wanted a very low center of gravity, it ends up being a bit like a canard. The takeoff is the so-called angled takeoff. And after the vertical landing, it still needs to lower the nose on the landing gear. We've flown this hydrogen-powered, hovering-capable, fast-forward capable platform for up to 4 hours over the Dutch North Sea and over the ocean, with winds up to 25 knots, so 12 meters per second, sea states, and landing with waves of 3 meters. So we think it's already real-world conditions, not just lab conditions, with payloads and autonomous flight. But in very turbulent conditions, if you have a lot of gusts, these long wings, they're not ideal while hovering. The last phase, when you want to land on the ship, for instance, there's a lot of turbulence from the ship, from the vessel. You would like to remove the wings, actually. If we look at our desires, this hovering and fast flight is pretty conflicting. During the landing, we ideally would like to get rid of the wing, because it's an aerodynamic surface that is picking up turbulence, which we'd rather not have. And while flying fast, we have all these motors that create extra drag, so that limits our maximum speed. To address this, we have proposed a rotating wing solution. It's patented, and we have a spin-off that is taking it into production. But the idea is that during fast flight, the wing rotates such that the motors are hidden in the fuselage to highly reduce drag coefficients at fast speeds. We also have stepper motors in to align them perfectly with the flow. And during hover, the opposite happens. Then the wing rotates over the fuselage like this. And the fuselage is damaging all the aerodynamic properties, which means that the biggest perturbation forces that are still acting on the system become much smaller. And by having this time not a tail sitter, but an in-plane solution, and having the biggest gust being horizontal, this device can handle much bigger turbulence while landing, while still being very efficient in forward flight. To show our prototype accelerating, rotating its wing, and then continuing as a fixed wing, we have this video here. And we have a bigger design already that is built around another hydrogen cylinder and a big payload compartment to do some real world testing. So this is what we think it looks like if you want to put available solutions of alternative energy in our electric robots. What comes out when you try to optimize hovering and fast flight while trying to achieve minimum mass? To look at this direction, I want to first look at nature. There's some beautiful examples of very small, lightweight creatures that can do very interesting jobs still. And that led to our design of the Delphi in 2005. The initial design goal for Delphi was to enter a building for flying outdoors pretty fast, and then hovering inside. but the technology to make small helicopters indoors in 2005 was not ready yet, while this flapping wing exhibits inherent slow hovering stable flight. So it flies at 0.5 meters per second thanks to an aerodynamic tail. It is completely stable like a fixed wing, even when flying super slow indoors. So it had all the advantages of helicopters and fixed wings at the same time. And on top of that, the wings gently bounce off obstacles because at the end of their stroke, they reach 0 velocity. And unlike propellers that cut quite a lot, so if you want to fly close to people, that's quite a bonus. Slow hovering flight and fast flight combined in a new design with flapping wings inspired by nature. The total mass is like the same as 4 sheets of paper, so 4 sheets of printer paper, about 16 grams, which typically is about 16 grams. It also has a camera, a video transmitter, and the first versions were processing the images off board. We made an even smaller one, which is like 8 foot, 10 centimeters, 3 gram. 3 gram is less than a sheet of printer paper. And for that weight, for that mass, you have a battery, a receiver, a controller, transmitter, motor controller, motor, gears, ball bearings, crank or rocker mechanism, double pair of wings, camera, transmitter, elevator with a coil actuator, everything. And to show that it actually flies, with a small video. The images are not HD yet, but it's from a few years ago. But it actually flies. It's a flying robot, very small. Then I already said that it's stably hovering thanks to this aerodynamic surface, but that's also a pitfall. If you're flying indoors and you're very light and there's air conditioning ducts and there's airflow, this aerodynamic stabilization is actually a perturbation. It would work much better if you remove the tail and have software or electronics stabilize the platform. So that was the obvious next step. Here we had 4 pairs of wings to allow real hover, this time standing still indoors and reacting to gusts while flying relatively fast. It is a small drone, only 30 grams, but it can reach speeds of up to almost 10 meters per second, hovering and fast flying. The next iteration had only a double pair of wings and featured in science because it was so agile that it could mimic some of the behavior that fruit flies do. And by systematically checking a wide range of flight conditions, we discovered a new aerodynamic effect that biologists had seen flies do that they could not explain. But it's not a robot yet, so we have an agile platform that can hover and fly fast indoors and outdoors. But how do you make it into a robot? And at that scale, we run into a problem. So if you have a 400-gram drone, flying takes about 250 watts. So 10 watts of compute is probably acceptable. But what about if you're much smaller and your flying is only 30 watts? Or even worse, if you're flying for 2 watts, you can never afford to carry so much CPU power. Aviation is still something where any power, any mass must be optimized to the fullest. And which is what we tried with our Delphi series. By giving it a set of nano eyes, I have some right here, the own designed PCB system, which merges with a CPU, with an FPGA, the camera streams on the back and then processor of the front. We managed to make a 1 watt intelligence system that allowed the Delphi to navigate indoors and then even detect doors, open doors, and fly from one room to the next automatically. As you can see, the images are not looking super beautiful, but for robots, the goal is not to make beautiful images, it's to react properly to the environment. And we've shown that this can be done perfectly well like this. So we used nature as inspiration for our robots, and then in turn provided new insights on how flights actually make such aggressive escape maneuvers and fly so efficiently. Last bit is, what about if we are interested in hovering, but also flying as fast as possible, but there are obstacles in the way? And there, efficient AI is a very hot topic of research. One of the tasks we're looking at is, for instance, this AI-based autonomous drone racing, where a robot needs to take off from a start podium, fly through a set of gates, and perform a mission completely automatically, based on camera images and some onboard sensors. And of course, all the processing has to be on board, a real robot. Then suddenly the wings don't matter, the agility, the aerodynamics are not the bottleneck. No, the bottleneck is that you get images like this. You need to understand what it means, where to go, where to move around. And the obvious solution to that is AI. And deep learning, to be more precise, has shown to be very good at solving this problem. But although there are a lot of companies working on it and the results are amazing, these are all technologies that are designed to run on data centers. And if we want to make robots, we still have a problem because the good algorithms are too heavy to put in our flying machines, especially our fast, slower drones. And if you're running a race and everybody has the same hardware, if you have a more efficient algorithm, you can run it faster, you can react faster, and then you can, in the end, win the race. So this has been our focus at the Micro Air Vehicle Lab from the start. Making these small robots is also a way to force ourselves to make things more efficient. And for the race I just mentioned, we proposed a solution that was super efficient, but would capture the entire problem correctly. Then we also made a very light neural-based controller to convert the best performing optimal control algorithms on board. Optimal control is amazing, but it's also very expensive. So in these flights here, we are mimicking the behavior of a very complex optimal solver using very light AI techniques and flying this particular drone. It doesn't look super fast because it's a slow drone, but it's really flying at the limit because there's always a few rotors saturating. So in terms of control theory, pretty complex. And that allowed us to become a world champion in AI-based drone racing with the DRL and AIRR competition in 2018. Last bit, so this AI, you can simplify the algorithms. It's one of the things we've done before. Now we're trying to do the next step. And I try to illustrate here how this deep neural networks work, with every dot here being a neuron, which is interconnected, which is represented by all the lines. And what traditional neural nets always do is compute layer by layer all the connections. So an image comes in, then all the neurons are activated, and all the connections are computed. While in reality, this network is multiplying zeros most of the time. According to our tests, more than 80% is multiplying zeros, but you can't leave them out. Otherwise, there are some situations that don't work. But it's not efficient. If you have a robot that needs to purge and observe for a long time, and the image doesn't change, it's completely inefficient because nothing's changing and you're processing all these connections all the time. But we are working now on a solution to this, which is found in neuromorphic hardware. Instead of computing everything all the time, we work with spikes, and the unit of energy is only when a spike is being sent. And spikes are only sent over connections that are active. And so you only use energy when there's a need. It has some added benefits, like you can process much more data. Because instead of sending all the pixels of an image, which is a lot, every time, if you only send the ones that changed, you can send way more. You have better temporal resolution. And that should also allow our robots to fly even faster or react to a person crossing the street while our defibrillator drone is approaching, and still react in time. So we have seen a few directions of how to combine hover and fast flight. One for efficiency with a lot of concepts, one for endurance with novel types of energy, at least in drones. What happens if you optimize for the smallest possible mass, where you still have a robot, and when you optimize for speed? Optimizing for speed turned out to be, at this point, still mainly an AI challenge that might change in the future, but if you have more efficient, lighter AI, you can run it faster and you can do more. Efficiency is a control, propulsion, and aerodynamics problem combined, but that, I would say that's yeah, that's the one that's more, that has more technological readiness. Endurance, it's looks simple to put hydrogen in a platform, but it turns out to be quite a safety challenge. Power is also not obvious, and a design will change dramatically for any type of different fuel that you put in there. In the future, we were still looking at possible alternatives. And once you minimize mass, then you have a very high benefit in terms of safety, but it comes with actuation problems, which we overcome by adding degrees of freedom in our flapping wings, and very severe computation limitation problems, which have prompted us to solve also the AI issues. And so together they address hopefully a lot of technologies that are also very important for manned flight, which, as you might have heard, is also part of my interest. I can't show this without thanking all my colleagues. Professor De Kroon is leading the MAVLab at this time, and project manager Wouter Mes is doing a lot of work to bring these technologies also to real life, to startups and spin-offs, and to hopefully also inspire industry with some of our solutions to come up with better platforms. I hope this is more or less the time you had that you had anticipated me to use, and if there's any questions, I would be very glad to address them. Thank you in advance.
That's a pretty impressive presentation and content. That's a lot of progress packed in a 35-40 minute presentation. That's amazing. Many of us have looked at or dealt with one or two of the challenges you talk about, but work on so many different aspects and the full spectrum of the challenges in this space. That's amazing. That's really impressive. No wonder, I always heard that Delft is a pretty amazing university, and now I know why.
Thank you so much. Well, it's of course thanks. A lot of credits go to all my team, and a lot of people worked on this for a few years, as you mentioned before. But we hope at least some of the solutions can inspire other projects to make important steps.
Open to the floor. Anybody has questions, suggestions? Try to understand more of what has been done on this space. While folks are thinking about questions, I do have one that you showed that one of them was like we call it, I guess, a scissor wing, that you turn 90 degrees on the wing and where the rotor is. Did I read it correctly? When you in hover mode, the rotor is on top of the fuselage. The wing goes straight through. Oh, the rotor is on the two sides, I guess.
Yes, there's a rotor. There are 4 rotors, and 2 are on a stick that protrude. If I'll try to get the proper slide for this. In 1 second. F5, and then I need to reshare probably. Sorry. So we have a lot of things going on here. We have 4 propellers. 2 of them are fixedly mounted at the bottom of the fuselage, which are hidden here and here. That's the 1 and 2.
Okay.
And then 2 are on a movable arm, which in forward flight hide in the fuselage, and in hover open up. So there's 2 hidden propellers at the bottom if you look carefully.
I see.
And now it's in quad rotor mode. We have 1, 2, 3, 4 propellers. And now it's in fixed wing mode, and both propellers are in the fuselage.
Huh.
The scissor wing.
Okay, okay.
And having the propellers in the fuselage, we could measure in the wind tunnel that the drag coefficient is really reduced, which is hopefully which which translates into much longer flights.
Okay, okay. So the fuselage has kind of open slots, so the propeller can rotate inside the fuselage, basically. Okay.
Yeah, we tried to
And
put some covers in there, but it turned out not to be very useful at this scale.
Okay.
The added mass doesn't weigh against the aerodynamic benefits, because you're in the boundary layer anyway.
Ah, okay. Interesting. Yeah, I always thought about the scissor wing could in some way apply in the VTOL world. That I guess you already done it. So it's a pretty neat. That is neat. Stephen, are you do you have questions?
I do. Can you guys hear me?
Yes.
Thank you, Christophe. It's a great presentation. I was curious, I'm interested in your spike processor. Did your team develop that silicon? And the question is really, is it scalable to real world applications and not a laboratory setup?
Yeah, very, very interesting question. So the project I described here is with a product that we did not make. It was made by Intel, and it's called the Loihi. The Intel Loihi chip. Intel is creating the silicon. We have made some FPGA boards initially ourselves that do the same a few years ago, but now we're translating to real silicon, and to make this into mass production. It's not something a university can easily do, and then we have partnered up with a product like Intel, but there's more and more that do this now. So there's not a monopoly. We think it's still early. We don't get the same quality of results in spiking nets than in traditional neural nets. However, because they're so much faster and orders of magnitude more efficient in terms of energy, it's still on a par, because the neural net technology works a bit less well in spikes, but you have way more speed, so they're on a par at system performance. But there's still a lot of research to be done. I would think it's still a few years before you can put this into bigger into commercial applications, basically.
All right, thank you.
Hey, Bruce?
Yeah, so I'll just love the oblique flying wing work. It's so different from the previous when we're looking at supersonic aircraft and and high performance gliding. So I really like the use of that. Question: where do I find out more about this? Find some of your papers and such. Definitely a lot of interesting stuff. And yeah, I agree. As Johnny said, it's a lot of work in a lot of areas. So totally fascinated by what you guys are doing at UAVs there.
Yeah, thank you a lot. Thanks a lot. I've tried to put the links to the papers under nearly every slide. We publish everything. The goal is to advance for everyone and not to keep it. But if you need some specific references, I'm sure you can forward the email to the organizers, and I'll be happy to send you whichever paper is of your interest.
Sounds great. Thank you.
And Dr. Wagter, is it possible that you can make this presentation available in a PDF format so that many of our folks who could not attend today have access to it?
Yes, I could do that.
That would be great. Much appreciated. Yeah.
I'm not sure if the Zoom call was recorded. I got a pop-up initially.
It is recorded. Yes.
Yeah. I'm sure the slides by themselves say as much, but I am happy to share it. If we had a real in-person talk, then of course I would love you to show you the drones themselves.
Oh.
But over Skype it probably doesn't work as well.
Well, next time I come to Netherlands, definitely going to stop by your lab.
Yes, you're very welcome.
That's amazing.
Where to find Marilena, so you will be able to find our lab as well.
Absolutely. Okay, good deal. Good deal. I do have one more question. With a lot of advancement in the AI, different versions of AIs and so on, is any of the progress we've seen in the last 6 months or whatever seem to be significant compared to prior years? Any of them you think are more meaningful or valuable for what all these topics that you're working on?
So yeah, AI has changed a lot, and it keeps changing a lot. To me, AI, 2012 is the year that AI started to work. That's when ImageNet beat humans in categorizing images. The year before, some top AI scientists were still saying it's 50 years out. But suddenly we noticed that this very simple idea of taking a neuron, which is just doing a sum, it's a very, very, very simple principle, and then adding some nonlinear activation on that, and then minimizing the total energy. So what they did in 2012 is manage to train also the deep layers. That was a game changer that has driven all the developments that you see now. Even the large language models are just a byproduct of the same idea that you can do deep training. Mathematically, it's really not logical that if you have hundreds of layers of neurons and you just do a gradient descent to find the optimal solution, if you have thousands or millions of parameters split over all these layers, it's mathematically not obvious that you can find a proper weight everywhere. And that was solved some years ago. All the developments we see now is, in my opinion, a scaling up. It's getting bigger and bigger. You have more neurons, more data, more neurons, more data. That's what brings the GPT, the generative pre-trained transformers. It's not really new technology. What is really helping a lot is this new hardware to make it faster, so the NVIDIA chipsets. But the biggest, I think it's more fine-tuning of an existing solution. And what the recent developments in large language models have only shown is that a simple trick like predict the fourth word if you're given 3 words is apparently sufficient to develop reasoning, because you can't remember 1 + 1 is 2, 1 + 2 is 3. So at some point it needs to learn to count automatically just by looking at the data. These developments are going very fast. So I'm quite convinced that the world will look differently in 10 to 20 years. But there's no magical new development. It's more fine-tuning of the same principle. AI now works. We can learn deep, very deep, very large models, which do smarter and smarter things.
Sounds good.
Johnny,
Stephen?
are you plugged into the Electric Aircraft Symposium in the, I'm wondering if they have locked in the agenda, because I can talk to either, Ken Swartz or, to see if we can get Christophe as an invited speaker. I don't know if you're interested in traveling to the States during late July, but I think the electric aircraft symposium would really get a kick out of this paper, and it would be a great it would be probably the highlight of that conference, honestly. So I can see if I can pull some strings and get you on the docket, if that's interesting to you.
Let's talk to Mike and Tom and other organizer for the conference, and I think that's a great idea. I mean, the content will be of significant interest for pretty much all our attendees at the symposium. So let's follow up on that. Yeah, Stephen, I think that's a great idea. The content is it takes more than just one session to absorb, obviously. And it would be great to be able to be in person, to have a more in-person interactions and dialogue and discussions and brainstorming. Yeah,
right.
That would be.
Well, I think that it's inspiring. What the work that you're doing is inspiring, and I think it will, inspire others to advance the technology. So
yeah, no, good idea. Let's do that. Let's follow up on that one, see whether that's a possibility still, whether the agenda is already locked in. Yeah. Let's find out. If not that, then we'll find another platform or opportunities. I agree.
Well, thank you very much for the kind words. And of course, if I can contribute, I would gladly try to fit it in, if able. Thank you very much for the kind words.
And of course, if you manage to get to that Electric Aircraft Symposium, you get to attend the Oshkosh right after that. So, hey, yeah, nothing can beat that one, right? Yeah. All right. So, well, thank you again. This is amazing. And thank you, Dr. Povell, for make the arrangement for you to be the speaker. I really appreciate this. So we're at our time. Thanks, everyone. And we'll talk to each other next month. Have fun, everyone. Thank you.
thank you.